Hello, this is a continuation of where we left off. From the first part, we covered the ideal gas law and the kinetic theory of gases, and we also briefly covered the first law of thermodynamics. In this part, we will cover the last section of the last part, and that is the second law of thermodynamics. And then we will devote the rest of the lecture, video lecture, for solving problems. I have at least 3 problems, 2 of them for the homework and 1 as an example from chapter 15. So let's begin. So we begin with the second law of thermodynamics. And second law, before we talk about the second law, we need to cover, we need to talk briefly about what is meant by the heat engine. The heat engine is basically a device that converts heat into a useful form of energy, such as electrical energy or mechanical energy or some other stuff. The first heat engine that comes to mind when I hear the term heat engine is basically the car engine. The car engine is what we call an internal combustion engine, ICE, where basically you have fuel comes into the engine, it's burned, and as a result of that, it converts part of that heat that's generated from the burning fuel into mechanical energy. And the mechanical energy here, of course, is the motion of the car, or the spinning of the wheel, if you will. Okay, so that's basically what a heat engine is. Another example is the power plant. Power plant is basically the plant where it generates electricity. You know, right now you are watching this video, your computer is plugged into electricity. Well, what does this electricity come from? Well, it comes eventually from a power plant. So what does the power plant do? At least the classic power plants, they have coal, and the coal is burned, so it generates thermal energy. This thermal energy is used to heat up water. The water turns into steam, and then the steam is directed to blades of a turbine, and then it sets the turbine into spinning or rotation, and finally mechanical energy is generated, and that mechanical energy is used to derive the electric generators to produce electricity. So basically, the power plant starts with the heating of coal, so you have thermal energy, and then this thermal energy eventually is converted into electrical energy, which is what, that's why we have electricity in our homes, for example. Okay, so those are the 2 examples of what we meant by heat engine. So you start with heat. Somehow you need a working substance, such as water turning into steam or fuel burning, and then from that heat is converted into something that is useful for us, such as a motion of a car or generation of electricity. Okay. So I wanna show you how this can be drawn in a diagram, how it works. So what you have is so let's take the example of the car, because we are all familiar with car engine. So imagine that this is what we call a heat reservoir. If I can spell it. I can't write the H. Heat reservoir. And this heat reservoir, I'm going to make it a bigger box. Just like that. There we go. So heat reservoir. When we say reservoir, means a source of heat that doesn't end, or there is just too much of it. Okay. In other words, if you take, no matter how much heat you take from it, it doesn't affect its temperature. Okay, it's called a reservoir. So anyway, we have a heat reservoir, and it is at some temperature T sub H, H for hot. So this is a very hot temperature. Think of it like this is the burning fuel for the car. And what happened? The burning fuel goes to the engine. Here is the heat. is inputted, if you will, input or enters the engine is the heat, the hot, that is very at high temperature. Here is the engine, which moves the cylinder. Okay, this is the engine. And as a result of that, the engine will do work. So work come out, which work, what we mean by work, is the motion of the car, right? The spinning of the wheels, if you will. And of course, there will always be a leftover heat, heat extraction or heat expelled at a lower temperature. We're going to call it Q sub C, C here for cold, and it goes to the environment or the cold reservoir. Okay, this is a temperature that is much lower than H. So we're going to call it T sub C. Okay, so that's basically the diagram of how a heat engine would operate. Okay, so we have here. So let me just try write it in bulleted items. So here we have a heat engine carries a working substance. For the case of a power plant, that would be the water, for example. For the case of the car, that would be the fuel, the gasoline, through a cyclic process. Cyclic means a process that repeats itself over and over again. Okay, so a cyclic process, and then you have three things here. One, you have heat is absorbed at high temperature which is basically here. So heat is absorbed at high temperature right here. This is the heat that is absorbed at high temperature. Okay, remember, this is the burning of the fuel in the car, which is the heat reservoir, and then this heat comes into the engine to move the cylinders up and down, you see what I'm saying? And as a result of that, the cylinders are moving now up and down, and they are connected to the differential, and then a transmission. Eventually it will spin the car. You got that? So that spinning of the car, or the motion of the car, is what we represent it as the work. Okay? But not all this heat, QH, turns into work. This is what's interesting, okay? Only a fraction of it, as a matter of fact, is about maybe 20% of it. The rest of it is just wasteful energy. So the rest of it, which is the wasteful energy, is right here, what we call Q sub C, because this is a much lower energy, much lower temperature, but it's still a lot of heat, and that heat is extracted or expelled out of the engine, and it goes to the cold reservoir. The cold reservoir in this case would be the environment outside, the exhaust system, okay? So heat is absorbed, so let's go back. So the heat is absorbed at high temperature, and then two, you have work is done by the engine, okay, which is basically right here, okay? And the third one, we have heat is expelled by the engine to the reservoir at lower temperature. At lower temperature. Okay? That's basically how the heat engine operates. You got that? All right. And keep in mind, this, of course, this is a cycle that repeats over and over again, okay? It repeats, 100 times. When you look at the RPM in your car, say 2,000 RPM or something like that, that repeats 2,000 times a minute, okay? So this is a cyclic process that goes over and over again. It keeps repeating, okay? That's why we call it a cyclic process, because it's a periodic mode. It's a periodic process that keeps repeating itself over and over again, okay? All right. So because it's a cyclic process, okay, and if I would draw on the PV diagram how this process looks like, try to make it as vertical as I can. So if this is the PV diagram right here, it's going to look something like that because it's cyclic and it repeats itself. So that means it's not an open process, it's a closed process. So it'll look something like that, if you will, where it repeats itself and where the work is basically the area of that is enclosed by the curve here. That's the work right here. Okay? So it's a cyclic process. In other words, I start at some temperature T hot, and I end up with a temperature T hot. You see what I'm saying? So in that case, what I'm trying to say here is that because I'm starting with one temperature and I end up with the same temperature, so that means overall the change in temperature is zero. There is a temperature, but the change in temperature is zero, and therefore delta U, there is no change in the internal energy of the system. Okay, that's the idea here, is that for a cyclic process such as a heat engine, that the internal energy, the change, not the internal energy, there's a lot of heat there, but the change in the internal energy does not change at all, and therefore it's equal to zero. You get that? So let me go back and apply all of that with this diagram in mind. I hope you've written it already. I hope you've written it down already. And let's apply the first law of thermodynamics. As you know, the first law says delta U equals the difference between Q and W, right? Now the Q here, remember this Q is always the net Q. Okay, here we have two Q's here. The hot reservoir is giving off a lot of heat to the engine, and much of that heat really is expelled useless, okay, and only a small fraction of that heat is used to do work. To do work on the engine, on the car, excuse me. And as a result of that, so when we look at this Q, it's basically the net between both of them. So here Q, or Q net, let me just call it, it's basically Q hot minus Q cold. Okay, and of course we have, since it's a cyclic process, delta U is equal to zero, and that tells us basically that let's see, have a zero, I'm here. So 0 is equal to Q minus W, so Q equals W, and that basically looks like QH minus QC equals W. We come up with this interesting formula. Okay? All right, so what does all this means? As I said, part of only a small fraction, only a small fraction of the heat here is used to convert into work or useful form, and the rest of it is expelled to the environment. So now I want to define something called the efficiency of the engine. E, or some books to use epsilon, the Greek letter epsilon. In our book we use E. The efficiency of the engine is basically the ratio of the work to the heat absorbed at high temperature by the engine, okay? Which is basically Q sub H, the one we just talked about, okay? So efficiency is basically equal to the work divided by QH, okay? Now, we just said that the work, here it is right here, the work is equal to the net heat, which is the difference or the increment between the heat absorbed minus heat expelled. So I can plug it in there. So that's going to be heat absorbed minus heat expelled divided by heat absorbed. And if I just do the algebra, I'll end up with this. 1 minus Q sub C over Q sub H. And I end up with this interesting formula, that the efficiency of an engine is equal to 1 minus Q sub C over Q sub H. Okay? This is a very important formula in engineering, which basically tells you what fraction of the heat absorbed, okay, what fraction of the heat absorbed has been used as useful energy to get the car, say, to move. Okay, what fraction of that? 20%, 30%, 40%, whatever it is. Okay, so the larger the percentage, the more efficient the engine is. You see what I'm saying? Think about it. Imagine if Q sub C is equal to 0. So let's go back to that diagram. Imagine that every joule of energy that is absorbed or taken from the hot reservoir into the engine, every single joule of energy there is used to get the car to move, and no expelling of that, we would have a perfect engine. You see what I'm saying? But that's impossible. Okay? So if Q sub C is equal to 0, that means E is equal to 1, and that's impossible. Okay? Theoretically impossible. So we say that no heat is expelled at all, QH is used into work. Okay, in that case. And we call that the perfect efficiency. Okay, we refer to it. So E equals 1 is perfectly, or an engine that is perfectly efficient. Okay. So what does the second law says? The second law says it is impossible to construct a heat engine that is, sorry, let me just put it in a different way. It is impossible to construct a heat engine that operates in a cycle with 100% efficiency. Basically, in plain English, it's impossible to manufacture or to construct an engine that is 100% efficient. It's impossible to have a heat engine where all the heat absorbed is completely converted into work. There will always be an amount of heat that would be expelled or unuseful, that is not used. You see what I'm saying? In other words, there is no perfect engine, and that would be another way of writing that. So no perfect engine. That's basically what the second law. So the second law is not really a law of nature. It's more a law of impossibility. Okay? So it basically says you can never, ever win when it comes to converting energy from one form to another. There will always be an amount that you cannot convert into something that you want. Okay? All right. Let me show you an example how that works. The example says find E, the efficiency of an engine that introduces 2000 joule of heat during a combustion phase and loses 1500 joule at exhaust. Okay? So what he's saying, let me go back, let me draw the heat engine diagram. So here we have, here is the heat reservoir, the hot reservoir. Here is the engine right here. Work is coming out of it, right? Here is the QH, the heat absorbed. Here is the heat expelled. And here is the cold reservoir. Right? Okay, so what he's saying here, what is the efficiency E of this engine right here? This is the engine. What is the efficiency of this engine that introduces 2000 joule of heat? So basically this QH is equal to 2000 joule. During a combustion or burning phase and loses, so it is here, so it loses 1,500, not 200, 1,500 joule there. So what is the efficiency of that engine? Now, of course, we can easily find the work. What is the work here before we calculate the efficiency? What is the work? Well, the work is the difference between QH minus QC, correct? So that will be 2,000 minus 1,500, and that will be basically, of that 2,000 joule of heat, only 500 has been converted into useful energy, such as work or motion of a car or whatever it is, or electricity for the power plant case and so on. Okay, so this is basically what the work is equal to. Now he's asking for the efficiency. We have two formulas to deal with, or one of them. You can pick whichever you want. I can either use this one since I have the work already, or I can use this one. It really doesn't matter. You'll get the same answer, right? So we can use either. Let me use the second one just for the sake of, since I already used W here. So here we have E is equal to 1 minus Q sub C over Q sub H. And that will give me 1 minus Q sub C is 1,500 divided by 2,000. And when I calculate that, I will get 0.25 or 25%. Okay? And there we go. That's the efficiency of the engine. What does that mean? It means only of this heat absorbed, or let's say the heat given off by the hot reservoir, 2,000 joule, only 25% of it is used as useful work, and a whopping 75% of it is just waste. Okay, just go to the environment. Okay, actually, this is a very efficient engine. Most engines are in the range of 20% or even less. Okay, car engines are the same way. I would say about, if I remember calculating some engines for cars in the range of 20%, maybe 25% if they're really good, but around 20%, give or take. Okay, here's a side example that is a continuation of this one. He says, if an engine has an efficiency of 20%, okay, and loses 3,000 joule at exhaust. Question, how much work is done by the engine? How much work is done by the engine? Basically, he wants to know what is the work. Okay, if we know that the efficiency is 20% and loses, he said loses this to the exhaust, which basically this is Q sub C, correct? So we have here Q sub C is equal to 3,000 and the efficiency is 0.2, right? So I can use the same formula. So I have E equals to 1 minus Q sub C over Q sub H, and then I just plug in what I have. Of course, this whole thing is equal to 0.2, right? And then I would just plug in what I have. Let's see. Let me do the algebra. Let me solve for QH. So I can move this one here to the other side. So if I do it in one shot, I will get something like this: Q sub C over QH equals to 1 minus 0.2, and that's equal to 0.8, and therefore that's equal to 0.8. So that will be QH is equal to Q sub C over 0.8, and I can just plug it in. So I have 3,000 divided by 0.8, and therefore QH is equal to, if I do the calculator, I'll get 3,750 joules. So this is how much heat is absorbed by the engine, okay? Of course, extracted or expelled 3,000. So the work, the actual work is, you can just simply take the difference between them. So it's just QH minus QC. So that'll be 3,750 minus 3,000. And that's basically the work that is actually, oops, joule, not W. I'm trying to erase it again. It's not working. Sorry. Oh, it worked by itself. I didn't touch it. I think I need to restart the whole computer maybe. Anyway, joule right here. There we go. So that's the work. Okay? All right, good. Let me do, that's basically what I wanted to talk about as far as the second law of thermodynamics. Your book covers the Carnot cycle. That's on, I'm trying to look it up for you. It's on section 16.6, the Carnot cycle. The Carnot, or Carnot is French, cycle. We're not going to cover that because this is more of an engineering application. And I know most of you guys are in the medical profession. I don't think you need this stuff. So I'm not going to cover it. If you need to learn about it, you can probably just read up. You'll have enough background to understand it on your own. Also, I am not going to be covering entropy. So we will basically, this is basically the material that I wanted to cover as far as chapter 16 is concerned, okay? So let me do, I have at least 3 problems to work with you on. So let me go back to, let me see. These are important examples or problems, so please pay attention to them. 2 of them are coming from the homework, and one of them is an example in the book, example 15.10. Let me look it up in the book, and then my hard copy here, and then I'll, because I want to know the page number. Sorry, bear with me. There we go. Page 483. And this is all about the PV diagram, okay? The PV diagram is extremely important. I put a lot of emphasis on it, so please make sure that you understand this diagram. And I have actually 3 problems to work on in this video lecture on the PV diagram. And we begin with this one. Okay, let me make it a little bit bigger for you. Okay, it says, in this more complex example, we will carry the several thermodynamic processes in a row. As we proceed, we will keep track of the flow of heat and work energies. And by the way, when we talk about PV diagram, you want to think of the first law of thermodynamics. Okay, so delta U equals Q minus W. And PV diagram basically is concerned with finding delta U, finding W, and finding Q. That's that's basically what it's all about, 90% of the time. Okay, so it's all about the first law of thermodynamics. All right, he says, So what you're looking at, as you can see, you have here a process, and I don't know if you can see that on the screen or not, but in the book it's very obvious. If you follow my mouse here, the yellow or green circle that I have here, it is from A to C to D. That's one cycle, if you will, or one process. And then the other one, this is in dark blue, and then the other one is in light blue. And then from A, B, and D. Do you see that? So he should have put different colors, but he put them in both in blue, which is kind of silly. Anyway, he said a series of thermodynamic processes is shown on the PV diagram. In process AB, this way, 150 joule of heat are added to the system. So from here to here, 150 joule is added to the system. Let me stop right there. What kind of process is this from A to B? We talked about it in the previous video. And this process is isochoric or isovolumetric. Look at that. The pressure have changed from A to B, from 3 to 8, if you will, right? But the volume is the same. It's still this number, 2 times 10 to the negative 3. So that's isovolumetric. Isovolumetric is always vertical like that, whether it's up or down. Okay, so that's isovolumetric. This is important to know. Okay, now if you go from B to D, what is that? Well, that's isobaric. Why? Because as you can see, the pressure is the same, whether it's on B or D. However, the volume have expanded. See what I'm saying? Now from D to C is what? Is isovolumetric again. It's the same volume. The pressure drops down if we go in this direction, of course. Now from C to D, or let's say from A to C, this is isobaric again. The pressure is the same, 3 times 10 to the 4 Pascal. But the volume is larger, from 2 to 5. You get that? So this is very important. So once you see a PV diagram, the first thing you do is kind of follow with your eye what kind of process it is. Is it isobaric, isovolumetric, isothermal, adiabatic, whatever it is, okay? All right. So we have a series of thermodynamic processes shown in the process AB, and I believe he wants from A to B like that. 150 joule of heat is added to the system. So what is this number? That's Q. Make sense? Because it says heat added. Remember, there are three variables here. Delta U, internal energy, Q, and W. W is work. Internal energy is U. This one is heat added, so that makes it a Q. And in process BD this way, in light blue, he said 600 joule of heat is added. So that's another Q. Okay. Find the internal energy change in the process AB. We want to know what is the internal energy from A to B. And then part B, he says, find the internal energy change in ABD, the entire process, which means you want to add up the internal energy from A to B plus the internal energy from B to D. You got that? All right. And then C, he said, what is the total heat added to ACD? So he's going to go in this direction now. ACD. In other words, you want to get the total heat added, which means you want to get the Q from A to C and the Q from C to D. You see the plan? Okay. Let's see how we do this problem. I'm not going to follow his. I'm just going to, I have my own, so I solved it my own way. So I hope this mine is clear. If it's not, you can read his solution. I'm sure it's similar to mine. Okay. So let me just put this in writing here. The Carnot cycle, we're going to skip it, all right? Okay. Example 1510. And I'm going to draw the diagram. Sorry for the crooked lines. I would rather be using chalk. So this is C going this way, going this way. Everything is, all of it is A to B, D, excuse me. And that's B, and this is A. And the number here is 3, and the number here is 8, okay? And then the pressure, and you want to multiply all those numbers by 10 to the 4th, okay? Pascal, the unit. Make sure the units are proper. Very important. If you see centimeter cubed, you want to convert. So this is a meter cubed. And this number right here is 2. And this one is 5. And they're all multiplied by 10 to the negative 3. Okay? There we go. All right. So let's write down what's given to us. He says the process AB, I have 150 joule added. Okay, I'm going to keep that added to the system. Okay, and then process BD, 600 joule is added. Okay, remember these are Q's. And what he wants what is delta U in AB? That's the first question. And what is delta U, the internal energy, in ABD? Okay. And then the third question is, what is Q in ACD? You got that? Okay. How do we do this problem? Take notes. Okay, let's begin with the process AB. Okay, we are basically following it from here to here. This is isovolumetric. And we talked about that. Go back to the previous video to see what that means, which means delta V is 0. What are the consequences of delta V 0? The work is 0. This is always the case, okay? Why? Because I told you before, work is associated with volume. If there is no change in volume, there is no work done. You got that? Very, very important. So work is 0. In other words, if I am using my first law of thermodynamics, W is 0 for isovolumetric. You got that? So I'm left with delta U equals Q. Well, my gosh, he said Q is equal to 150 joule, correct? It's right here. That means delta U is also 150 joule. Isn't that simple? That's it. You're done with the problem with this part. He said find the internal energy for this process AB. Okay, good. Part B. Find the internal energy for the process ABD. Let's go back to the diagram. ABD. Well, I already got the AB. It is equal to 150. I just got it, right? It's right here. All I need to do is to get the internal energy from B to D. Once I get that, I add it to A and B, and I get the process for ABD. You see the plan? Okay. So let's get the process from B to D. So B to D. Well, that's isobaric. And what's so special about isobaric? Isobaric, the work is equal to P delta V. Again, we talked about that. Okay, P delta V. This is for BD. Let me just put a BD here just to remind myself. So what is the pressure here? Well, the pressure is 8 times 10 to the 4th. Correct? And then delta V, this one, whoops, sorry. Delta V here is what? Is basically the difference between, so remember it goes from B to D, so that from 2 to 5, so that means 5 minus 2 to the power of negative 3. You got that? So that's what we're going to do. So in this case, the pressure, whoops, I forgot what pressure is, 8. So it's going to be 8 times, you know what, I'm going to put it, it's just kind of, I'm going to restart this thing. It's just not erasing well. Sorry, I'll be back. There we go. And then restart. There we go. It should work. It always works. Okay. So we have here WBD is equal to P, which is equal to 8 times 10 to the power of 4th, multiplied by delta V, which is 5 minus 2 to the power of 10 to the negative 3. And then I calculate that. And when I calculate it, I get, I'm using my calculator, 240. There we go. So the work done BD is that? Why did I get that? Well, I want to use the first law of thermodynamics to get delta U. But hang in there in a minute. Hold on. What does it say for the part B? He said by the internal energy change in ABD. Okay, let's hold on to the delta U. Let me jump to C and I'll come back to B. Okay, let me jump to part C. That is. Now part C, he says, what is the heat added to for the process ACD? In other words, going this direction. ACD. Got it? This direction. Maybe I should put it in a different color. Do you mind? Let me put it in a different color. Should have done that earlier. There we go. Is that better? Okay. Okay, so let me ask this question. What is the total work ABD? ABD. Look at that. The total work ABD. Okay? What does that equal to? Well, the work AB, sorry, I wanted to say something. So the total work ABD, remember, whenever you have a PV diagram, an easy way to calculate work is simply calculating the area under the curve, okay? And that would be it, basically geometry. You just look at the area under the curve, what is it equal to, and it's really that simple. You just calculate the area under the curve. That would be one easy way to do it. However, I mean, we already have the numbers. We already calculated the work BD right here, and we said that the work is 0 for AB, remember? So the work for AB is 0 because it's isovolumetric, and from BD I already calculated that, and it is equal to 240. So the work ABD is basically the sum of those two. So the work ABD is equal to the work AB plus the work BD. Well, the work AB, because it's isovolumetric, such a big word, is 0 plus 240. So the total work really is 240 joules. Whoops, 240 joules. Okay, so what is the total heat now? I'm talking about ABD. Total heat ABD. Go back. A, B, D. The total heat. Total heat, basically, the heat from A to B plus the heat from B to D. Well, we already got them right there. You just add them up together. So the total heat here, ABD, is equal to the heat from A to B plus the heat from B to D, okay? And that's equal to 150 plus 600, and that'll be 750 joule. Okay? Next. Now, what is the total internal energy ABD? Total internal energy, well, I can just go back to my first law. It says the total internal energy is Q minus W. For our case, the total internal energy ABD is equal to the total heat added ABD minus the work ABD. Make sense? So I have them both. So ABD here is 750 for the Q. Yes, that is true. For 750 minus the work ABD is right here, guys, 240. And when I calculate the total internal energy, it will be 510 joule. You see that? Okay. Now, what is the total work for the path ACD? the total path the total work for the path ACD. Okay. Well, let's keep in mind. Look at that. From A to C, that's an isobaric. That means work is equal to P delta V. But from C to D, that's the isovolumetric, so there is no work here. The work is 0. Make sense? So if I go back, so the work, total work for path or process ACD is equal to, is the work from A to C plus the work from C to D. Well, C to D is 0 because it is isovolumetric, isochoric, right? So this becomes, and AC, how do I calculate that? Look at it. Remember I told you the work is basically area under the curve? Well, from A to C, well, I can just calculate the area under the curve. Let me use a different color and show you what I mean. Let's pick green. You can do it this way, guys. Look, you can just, this is the from A to C, right? This area under the curve. So you're looking at a rectangle. If you calculate this area, you basically get the work AC. Just a rectangle, right? So it is just length times width, if you know what I mean. So the length, let's assume the length is this one. So that's 5 minus 2 times 10 to the negative 3 times the height, if you will, or width, whatever you want to call it, 3 times 10 to the 4th. That's it. And you will get the area which is equal to the work. You got that? So here the work so the area, this is basically area under curve. So that will be equal to 3 times 10 to the 4th times 5 minus 2 times 10 to the negative 3 plus 0 for WCD. Is that what I'm saying? So, and there we go. We do the calculations here, and I end up with 90 joule. Okay. So the last part, what is the heat added for the process ACD? In other words, what is this? Well, it is according to the first law of thermodynamics, delta U is equal to Q minus W. So in this case, Q is equal to delta U plus W. So that will be, for our case, QACD is equal to delta UACD plus WACD. Is that what I'm saying? I already got WACDs right here. Well, what is delta UACD? Here is something interesting. Watch. The internal energy, okay, this is important. The internal energy is independent of the path. In other words, let's say I'm going to go from A to D, correct? Well, I have two paths. I can go ACD, or I can go ABD, okay? Or I can even go any other path. Here is another path if I want to. I can go crazy. I'm going to make this path, okay? Any path that I want, as long as I am at the same starting point and the same ending point, the internal energy is always, the change in the internal energy is exactly the same. Got that? Let me repeat it again. The change in the internal energy is independent of the path. Well, guess what? We already calculated the internal energy from the process or the path ABD. We got that number. It's right here. I thought we did. Didn't we? There it is. ABD. It's 510 when we followed that path. So what is the internal energy ACD? Well, it's got to be the same. You got that? So delta U, this is very important. So delta U is independent of the path. This is very important. It'll save you a lot of time, a lot of calculation. So delta U A C D is basically equal to delta U A B D. Okay, so now I go back to this. So Q A C D is basically 510 plus A C D, which is right here on the top right there. So that will be equal to 90 to 90 joules, and that's equal to 600 joule. And there we go. Okay, I hope this example is beneficial for you. You've learned a lot from it. Okay, I have two more problems. I'm looking at my notes here. I want to do homework problem number 51 and 52. Let me find them in the book. Oh, chapter 15. On page 494. Let me go to the book. 494. There we go. 51 and 52. I'm going to do both of these. They don't look bad. You don't need to. I'm going to give you 53 because it's isothermal. I'm not going to worry too much about isothermal. If you see a curve like that, we're not going to worry too much about it. Only straight lines. Okay, see what I'm saying? So you may want to look into 50. Maybe I'll assign it as homework. I haven't assigned 50 yet as homework, but I may do that. But you may want to do it yourself. Okay, let's look at 51. Look at the picture here. Shall I make it a little bit bigger? Really big. Okay. So it says a PV diagram here. Look at that. Notice that before we read the problem. So you have two lines here, two paths, one from A to B to C. This one from B to C. As you can see, it's isovolumetric. There is no change in volume. This one, however, is neither, right? With an angle like that. The pressure is then Pascal times 10 to the fifth. So all these numbers are going to be multiplied by 10 to the fifth. Pay attention. The volume is fine. It's in the proper unit, meter cubed. And these are the numbers, okay? So the point A is 0.01, by the way. It's not 0.02. 0.02 is right here. This is 0.01. And then B is 0.07, okay? 0.06 is here. I already did the problem, so I've seen those stuff. And then B is 5 right here, the number. And then C, the number here is 8. Get that? All right. It said the PV diagram shows the process ABC involving 0.45 mole of an ideal gas. So N here, the small letter N, is equal to 0.45. Okay, A. What was the temperature? What was the temperature of this gas at point A, B, and C? A, B, and C. Okay. And B, how much work was done by the gas in this process? Okay, so we're going to get basically work ABC, WABC. And then C, how much heat, Q, had to be put in during the process to increase the internal energy by 15,000. So 15,000 here is the internal energy, delta U. Okay, so this problem is kind of cool problem. It's a combination of ideal gas law, PV equals nRT, and the first law, delta U equals Q minus W. Okay, let's get down to it. Again, I'm just going to draw it first. I hope you will you have your book open, your ebook is open on the side, because I'm going to make the book disappear. So at least in your screen, you are looking at the book. Okay. So I'm going to make the diagram. Already, I'm going to draw it here. So what I have in here. Here is the sketch, what we're looking at. Looks something like that. It's not going to be exact. You're going to have to forgive me. I'm trying to make it vertical. There we go. Okay, and the path, the direction of the path is like that. This is B, this is A, this is C, and then the point here is 8. And the point here is 2, and the point here is 0.01, and the point here 0.07, okay, and that's V meter cubed. And then this is the pressure, of course, and you want to multiply every number by 10 to the 5th in Pascal, right? And that's it. Oh, that is the point B right here. Whoops, I missed it. Anyway, the point B here is 5. Okay, there we go. Okay, so he's given to us N equals to 0.45 moles. Is that plural? I don't know. I'll just leave it plural. Okay, he wants excuse me. He wants the temperature at A, B, and C. Okay, how do we do that? Well, I think this is the easy part. We just go back to PV equals nRT, and R, of course, is the universal gas constant, 8.13. Excuse me, 314, and we have everything, really. I mean, here is the V right here, here is the P, so I just need to calculate T. So T sub A in this case is equal to, let me just solve for T first, sorry. So T in this case is going to be PV equal O divided by NR. So you know what, I'm going to do it only for one, and then you could do the rest of it. T sub A, which is basically P sub A, V sub A over NR. So P sub A for point A is right here, guys. P sub A is 2. So that's 2 times 10 to the 5th times V sub A, which is 0.01. Is that right? Divided by the number of moles, 0.45, and the gas constant, 8.315. Okay? And then you just calculate that, 3.314. I think your book uses 15, not 14. Anyway, so we have that, and then the answer is 535 Kelvin. You do the same thing for T sub B. I know you can do it. And the answer I got 9350 Kelvin. And then you do it for T sub C exactly the same way. And I got 15,000 Kelvin. Got it? Okay. Part B. He says, what is, I'm reading it from my hard copy, I hope you have the screen in front of you, how much work is done by the gas in this process, okay? So, how do we do that? Well, first of all, we can ask the question, is the work positive or negative? It's positive. Why positive? Because look at follow the direction of the arrows here. So it started from, if there is an increase in volume, okay, if the volume have increased, that means there is an expansion of the gas. Expansion means positive work. Get that? So there is an expansion of the gas here, so there's positive work. Got it? Okay. Also, heat added, positive. Heat subtracted or expelled, negative. You get that? All right. So here we have work is positive because gas expands from A to B. Now, to C, nothing happens. It's isovolumetric. The gas does not expand. There is no work. Instead of the work is 0, because that's isovolumetric. So basically, the work that I'm doing, really, is just the work from A to B. Well, what is that? What is that work? Well, the best way to do it is to simply, as I told you, get the area under the curve. Look at that. What do we have under the area? Let me analyze the area under the curve. Let me show you. Let me put a different color. The area is basically, we have a triangular area right here, this one, right? And then we have another area, which is, let me use a different color. Try to get that thing. Pink, how about pink? You like pink? So we have here, this area right here. So the total area, you want to calculate the area here plus the area here, and that area automatically will give you the work. Isn't that interesting? Remember, you want to calculate the area all the way down to the axis, always. Okay? So that's the area that we need. All right. So basically, the area of this rectangle, which is 0.07 minus 0.01 times the height, 2 times 10 to the 5th, plus the area of the triangle. What's the area of the triangle? 1/2 the base times the height. half the base, which is 0.07 minus 0.01, times the height, which is the number from here to there, which is from 5 to 3. You see the plan? Simple. Okay, let's do it. So this is basically, just I'm going to write it down to remind you, area under the curve. And if you do it, okay, I'm just going to write it down, and then you tell me, or verify for yourself that I'm right. I hope I am. Times the height, which is 3 times 10 to the 5th, and then plus 0.07 minus 0.01 times 2 times 10 to the 5th. And then you calculate that, and you end up with, I got 21,000 joule. There we go, that's the work. Okay. Part C, he says, how much heat had to be put in during the process to increase the internal energy to 15,000? Well, that's not bad, is it? He gives me delta U. Delta U is 15,000. And I already know what the work is. I just got it right here. So it's 21,000. So how do I get the heat? Well, go back to the first law. You see that? So we have Q equal to 15,000 plus 21,000. And then we just add them up together, and you will get 36,000 joule. Okay? And as you can see, it is positive automatically, which means the heat goes into the gas, or heat is added. Okay? And there we go. Okay, one more problem. Number 52. Right here, whoop, right there. Okay. It says let's look at the diagram. Always look at the diagram, study it, be familiar with it before you read the problem. So let's look at it. So here it is. Everything in Pascal and the unit are fine. Pascal and meter cubed. There is no multiples to multiply with. So here is the process begins in A to B to C. Look at the direction of the process, the path here. So this process right here from A to B is isovolumetric, work equals 0. As you can see, there is no area under the curve there. And then from B to C, there is a work there because there is area under the curve. And that's isobaric. And isobaric equal to what? P delta V, correct? So that's basically what we have. Then he has this dotted line. I have no idea why. When we read the problem, we'll see why he put that dotted line. All right. He says the volume of the air is first cooled without changing its volume and then expanded. So it has been cooled. So it was from here and it cooling the air without changing its volume. Got that? So that's an isovolumetric or isometric process. And then, I'm sorry, let me read it again. A volume of air is first cooled without changing its volume, okay, and then expanded from here, B to C, expanded without changing its pressure, isobaric, okay, as shown in the by the path ABC, okay. A, B, C parts, okay. A, how does the final temperature of the gas compare to its initial temperature? In other words, how does the temperature here, T sub C, compares with the temperature T sub A? One way to do that is to get the ratio. Okay, in other words, you want to get what is T sub A and what is T sub C. Get the ratio. That will be the easiest way to do it. Okay, not the difference. When you say compare, that means get the ratio. Get that? So I want to get the ratio of that. So what comes to mind here really is the ideal gas law, PV equals nRT. Whenever he asks you for T temperature, first formula that comes to mind is PV equals nRT. You're not going to use the first law. The first law does not have temperature in there, right? So that's the first thing that comes to your mind. So we're going to try it this way. So I'm going to put PV equals nRT for A and PV equals nRT for C, and then maybe divide it by each other and see what happens. That'll be the plan for me. Okay? So let's see how we do it. Again, I'm going to draw it first. Problem number 15.52. And the diagram looks something like that. I still don't know what that dotted line is, but that's okay. We have the pressure in Pascal, so everything fine here. And the number here is 3 times 10 to the 5th. And the number here is 1 times 10 to the 5th. And then the volume 0.02, 0.06. I'm copying all of that from my book. Okay, so he wants how this is A here, and this is B. How T sub A compares to T sub C, okay? All right, so at A, sorry, I don't want to use this at, okay. At A, P sub A, V sub A equals NR T sub A. And at B, at C, excuse me, it's P sub C, V sub C equals NR T sub C. Let's get the ratio. I mean, that would be, I mean, I don't have, I don't see 100% how to solve this problem, but I'm just using my common sense. If I get the ratio, probably something will happen. I'll end up getting something. So let's just get the ratio. To get the ratio, basically, let's say T sub C divided by T sub A, okay? So how do I do that? Well, before I do that, let me, from both equations, solve for T sub C and T sub A. So T sub A is basically P sub A, V sub A over NR, and T sub C is equal to P sub C, V sub C over NR. Now, so T sub C over T sub A, do the algebra, you're going to end up getting this. P sub C, V sub C over P sub A, V sub A. The NR will cancel out. Do the algebra and you'll see that. And guess what, guys? I have everything. Isn't that nice? There we go. See, I have the pressure at C. I have it right there. I have the volume at C right there. I have the pressure at A right here. And I have the volume at A right here. So all I need is just plug all that stuff in there, and I will get that ratio. And that will be the answer to this part of the problem. So P sub C here, again, I'm looking at the diagram. It is 10 to the 5th. Times 0.06 divided by 3 times 10 to the 5th times 0.02. And when you calculate that, I get 1. Isn't that interesting? What does that mean? So T sub C over T sub A is equal to 1. What does that mean? It means that the temperature at C and A are the same. Now you can pause the video for a minute. I want you to think about this for a minute. What does that mean? What are the consequences of that? Let's look at the diagram. So I started here, right? And according to the problem, I shrunk the volume of the gas, but I kept it to the same temperature. And then I increased the pressure of the gas from 0.02 to, excuse me, increased the volume of the gas at the same pressure. So the question is, what happened to the temperature of the gas? How did it change from A to C? Well, it turned out that it's the same. What does that mean? It means what I have done an isothermal process. Remember isothermal process? What's so special about isothermal? Isothermal means the temperature does not change. So this dotted line, the meaning of it, I'm going to put it in a different color. And I think I told you about it just a little bit. It's an isothermal process, so it's a curve going like that. try to make it a curve. It looks okay. It's an isothermal process. Okay, that's the meaning of it. That's the consequence of that when you see the same temperature, which means delta T is 0. Okay, so that's isothermal. Okay, great. Let's go to part B. Part B says, go to the book, how much heat does the air exchange with its surrounding during the process ABC? How much heat does the air exchange with its surrounding during the process ABC? Okay, so what does that mean? Well, okay, since it is isothermal, okay, what's so special about isothermal process? What makes it so special in terms of, if if I use the first law of thermodynamics, delta U equals Q minus W, if you remember, isothermal means no change in the temperature, and therefore no change in the internal energy. Delta U is 0. Aha, which means what? Q is equal to W. So if I find W, I know what Q is, or if I find Q, I know exactly what W is. Well, look at that. So I can come here, and if I want to get that the Q, for example, all I need is just to calculate the work under the curve, or the area under the curve, and I will get the work, and then that work is equal to Q. You see what I'm saying? Okay. Okay, let's see how we do this. Part B. So here we have, let me just write all that stuff down again. So TA equals T sub C, and therefore delta U equals 0. So AB, delta V equals 0, which means can't erase it again. There we go. Which means the work AB equals 0. Why? It's isovolumetric, correct? Okay. Now the process, or the path BC, we have it's isobaric, and so the work BC is equal to P delta V, right? Go back to the diagram. It's this one. So P, which is that, delta V, which is 0.06 times, minus 0.02. So I can calculate the work here, and that's going to be 1 times 10 to the 5th, multiply that by 0.06 minus 0.02, or simply, this is, what am I doing here? I'm basically doing the area of the curve, really. So I mean, that formula really just tells you the area of the curve. So either or, you can get the same answer. Anyway, so you will get here 4 times 10 to the 3rd joule. So this is the work BC. I keep writing A here. If I can only, I am sorry, the stupid thing. There we go. Okay, so there we go. So therefore, the work ABC, which is the work from A to B plus the work from B to C, and that's 0 plus 4,000. This is 4,000 right here, guys, right? And so in this case, the work is equal to 4,000 joule. And what is the heat? Well, heat is equal to the work, right? Because this is an isothermal process, since delta U is 0. So therefore, Q is also equal to 4,000 joule. Okay? And then the last part of the problem, let's go back to the book. He says, if the air instead expands from A to C, okay? go back. So from A to C, the air actually expands from A to C by a straight line, not the curve that we have drawn. So this dotted line, imagine, okay? How much heat does it exchange with its surrounding? Okay, how much heat will exchange? So if it is a straight line, okay, well, how much heat? Well, we still have the temperature A and C are the same, so we can say that there is no change in the temperature. Well, the change is equal to 0, and this means that the change in the internal energy is 0, and so Q equals W still holds. Sorry, I'll put the C here. So since TA equal to TC, therefore delta U is 0, right? And so this means from the first law of thermodynamics that Q equals W, right? This still holds, okay, despite what he's saying. This one still holds. So what is W? Well, W in this case, look at this. I'm just going to calculate the area under the curve. Let me draw it again. Sorry. Here it is. So what I have is this. So I'm going to be calculating the area under the curve here. Half the base times the height. You see what I'm saying? So in this case, it will be half the base times the height. So area under the curve. So in this case, W is equal to half times, if you look at the diagram, go back to your book and look at the diagram. So that will be, let me start with the bottom axis, in this case the volume. So that's going to be 0.06 minus 0.02 times the height, which is basically what? 3 minus 1. So that's 3 times 10 to the 5th minus 1 times 10 to the 5th. You see what I'm saying? And then we just do the calculations here. And when we do it, you end up getting 8 times 10 to the 3rd joule for the work. And therefore, Q, which is equal to W, is going to be the same number, correct? Joule. Okay? And I think that's about it. This is all I wanted to talk about. Please let me know if you have any questions.